All right, so yeah, if for those of you who didn't have a computer or cell phone with you, I encourage you to finish the teaching evaluation. Okay, so here's what we're gonna do today. Okay, we're gonna finish off this mechanical spring design, and we only have a little bit left now, and then we're gonna do a quick reviews on the whole sections that we learned after the midterm, and I'll say a few things about the expectation for the final exam. Okay, yeah, and that should be it. So we probably will finish early. Okay. So this is a quick review. Let's take a quick review of the mechanical springs out here. Okay. So what we did is basically we look at the terminologies associated with the mechanical spring. A number of things are very important because you need the parameters to do the calculation. What the wire diameter is, small d, right? So that you have to know it. Mean coil diameter, which is from the center of one side to the center of the other side. The coil pitch, okay, helix angle, okay, and then total number of coils, okay, NT. Total number of coils, as I mentioned in the last lecture. Okay, so you have got to be able to know how to count how many total number of coils for a given mechanical spring. And how do you count? Whenever you go 360 degrees or one turn, that's one coil basically. Okay. Yeah. And there's also another concept called the number of active coil. So number of active coil has to be different from NT. Well, depends, right? So only one condition is the same. So how do we know NA though? And that depends on how the coil ends, okay, for this mechanical spring. So we're relying on the table 10-1 to find the relationship between the total number of coil and the total number of active coil. So this is where you can identify the type of springs given. So look at the keywords in the question. The keyword is, the question says it's a ground and square, then your NT is equal to NA plus 2 or NA equal to NT minus 2. Right? So that's how you find the total number of coil first, and then find the total number of active coil NA next, right? By identifying the type of coil, the type of springs at here. And then we also look at the stress on the typical mechanical spring, compression type of mechanical spring. Analytical results is tau equal to Ks times this much at here, and Ks is what we call the shear stress correction factor. But experimental results suggest that we use a slightly different factor here, so which we call the burden stress factor. Okay, so this is basically the shear stress formulation that we'll use to do our calculation next. Okay, so tau equal to Kb times 8 times the force times the mean coil diameter divided by pi, and then the wire diameter to the power 3. Okay, so that's your stress existed inside the spring, and then the formula for the spring stiffness. So the formula stiffness can be derived based on the Constigliano's theory. One thing that I mentioned that you have to be very careful is, for this formula, the NA, right, is the total number of coil. Okay, so in the past I've seen people use total number coil instead of total number active coil at here. So this needs to be the total number of active coil for the calculation of the spring stiffness. Okay. So that's what we covered in the previous lecture, right? So we look at it, basically the stress. We also look at the spring stiffness. So the next logic step is we need to look at the strengths for a given basically a mechanical spring at here. Okay. Now for the strengths, okay, first of all, okay, before we talk about the strengths, we can actually talk about the material for the mechanical spring. Okay. So now the big topic here is the strengths, but the first thing, what are the typical basically materials to make a spring, right? This is basically, you need to look at table 10-3 for typical material. Okay, very common material. So here is a table 10-3. I'll show you what it is. So this is table 10-3. Typical material like a musical wire, okay, oil tempered wire, hard drawn wire, chrome vanadium, chrome silicon. Right. So these are basically the typical material for making springs here. Okay, these are all very typical high carbon and alloy spring steels. Okay. So take a look at that table for the typical material. And now what we're really interested is, because we find that on the cross-section of spring, what exists, the type of stress exists is a pure shear stress, right? So that's what we calculate, the pure shear stress. So what we really need is, we need to find the tensile strengths, okay, for the typical spring, okay. And from here we have another table to derive for allowable or permissible shear stress, okay. So first, let's look at how do I calculate the tensile strength. So tensile strength is basically SUT value, okay. And we use this formula here for calculating the tensile strength. And this formula derived experimental results. Basically, if you plot the tensile strength and the wire diameter using a log-log scale, and it basically gives us a sort of a straight line at here. Okay, yeah. So fundamentally, essentially, the smaller wire for the spring, the higher tensile strength, right? So smaller, the higher tensile strength. And this formula can be summarized as SUT equal to A over D to the power of M. The parameter D is the wire diameter. The parameter A and M, okay, A and M are from this table 10-4, okay, 10-4 here. And 10-4, if you look at it, basically first identify the type of material, and then look at the diameter, the range diameter here, okay, and then you look at the value A, okay, in the two different units, of course, okay. The parameter M, which is this column here, okay, yeah. So that's the way to find A and M. Then substitute over here, and you'll be able to calculate this SUT value. Okay. So this SUT can be calculated based on this table 10-4. It's very straightforward. Okay. So once you find SUT value, okay, and then what we need is, we need the torsional shear strength. Okay, SSY. And SSY, basically, as I said, because on the cross section of the spring, all you have is a pure shear stress. So if I want to compare the shear stress with strength value, then it got to be the shear strength value, SSY here, right? So this value here, we need to calculate that from the table 10-6. Okay. So 10-6, which give us basically a so-called permissible shear stress. Okay, this is what the table 10-6 will give us. Okay. Now 10-6 is this table right here. If you look at this table here, the first column gives us different type of material. So music wire and a cold drawn carbon steel, right? Are different hardened and tempered, and carbon and a low alloy steel. So different material in the first column here. The second and the third column here, okay? You got to read the title first. The first title here says before set removed. The second title says after set removed. Okay, I'll explain what set removed here. But for each column here, right, what it gives us is let's say for example here is 45, okay, for the set remove here. So what it does, it basically means is you use 0.45, okay, 45% times the tensile strength. Okay, so that's how you read from this table right here. So music wire, okay, for example music wire, then the SSY is equal to 0.45 times SUT. Okay, different material, hardened or oil tempered, and then it's 0.5, right? Then what does a set removed means at here? So a set basically means permanent set. Okay, so if you have a spring, and if you completely press it, and if you press it for a little bit long time, and then you let it go, guess what's going to happen? A very typical phenomenon, which is what? The spring doesn't go back to its original location, right? Yeah. So that's what we call a set, essentially. Just like our car, basically. After using it for a while, the spring are not as stiff as its original anymore, right? Yeah. So that's called the set. So from manufacturer point of view, you actually don't want that happen. Okay, so there is one way to prevent that from happening, which is called a process of set removal. So when you manufacture spring, if the user asks for spring, for example, let's say 20 centimeters, for example, right, as a free length, then what you can do is you can manufacture the spring a little bit longer than 20 centimeters, and then you completely press the spring, okay, by applying certain force, okay. And when you press for a while and then let it go, so the spring will basically stay at a 20 centimeters. Okay, so that's called permanent. Now that's called set removal process. Okay. Essentially, it causes some residual stress inside, compressive residual stress inside the spring. Okay. That's what the after set removal here. Okay, before set removal, which is essentially you don't do any process to the spring. That's what the before process removal here. And for this column here, sometimes it's also called as wound. Okay, so just wind it up as it is, right, and without any further process. So this column here could also be called as wound spring here. So if you're given a question, okay, and the question will specifically actually let you know what type of springs that you are dealing with. Okay. If it's an as wound spring, then you're essentially picking up a number from this column here. Okay. Okay. So that is how you calculate strengths, right? So now we're pretty much set. We have our stress, we have our strengths. So let's take a look at a quick look at an example here. Typical examples for the mechanical spring question here. Okay. Okay. So in this example, we're talking about ideal spring. Okay. There is also non-ideal spring that as an option here in my lecture notes. It's I put it as optional reading, so you can take a look at it. Okay, so non-ideal spring basically means, which is actually the common case, the beginning and the ending portion. So when you start to press it, right, there's a beginning section of a compression, and then when it completely pressed, okay, as a solid spring, the ending portion, okay, ending process. So they are actually non-linear. Right? So when you spring, the middle one is linear, so the force equal to K times delta X. Okay? But at the beginning, at the end, they're actually non-linear for the spring, so your force and the deflection are not linear, basically. Okay? For ideal spring, so we assume from the beginning till the end, when you're pressing it, and it's always a linear relationship between the force and the deflection. Okay? So let's say we have an ideal spring in here, and the spring is made of A228 music wire. The spring has a wire diameter 0.006 inch. Its outer diameter is 0.036 inch. Okay. The spring is square. It's squared and grounded. Okay. So the ending is squared and grounded. Okay. It has a total number of coil NT equal to 40. Its free length LO equal to 40. 0.63 inch. Let's say we assume a safety factor NS equal to 1.2. Okay. So the question here is it solid safe? Okay. Is it solid safe? So is it solid safe meaning when you completely close it, press and close it, will the safety factor be less than or be greater than 1.2? Right? That's what solid safe means. Okay. So essentially what we're trying to calculate now is the stress, the safety factor, when you completely close the spring at here, for this spring. Okay. Okay, so let's take a look at this kind of question at here. So very typical question. So first of all, we need to calculate the SUT value. Okay, so what's the tensile strength for the spring at here? I'm using that formula A over D to the power of M. Okay. So let's take a look at table 10-4 at here. Right? Table 10-4. Here we have a music wire A228. That's your music wire here. So M equal to 0.145. And we're looking at the unit is inch, so we should look at this column here. So A value is 201. The wire diameter is 0.006, so that's between this range at here. Okay? Yeah. So A equal to 201 and M equal to 0.145. So plugging these numbers, and D equal to 0.006. Okay, so you get 422 KSI at here for the SUT value. Okay. So now let's look at SSY value, so the shear strength, right? The shear strength. Now this question says ideal spring. Okay, let's see. I should put another condition here. So as wound, okay, spring. Okay, let's consider spring is as wound spring here. Then if it's a music wire, then the permissible stress or the shear strength is 0.45 times SUT. Okay, so that gives us 0.45 times 422, which is 189.9 KSI. So now figure out the strength now, right? So let's calculate the stress when it's fully closed. Okay, so a couple parameters we need, okay, to calculate the stress. So to calculate the stress, here's your formula: Kb, right, times 8 Fd over pi d cubed. Let's figure out each one of the parameters added here. Okay. Kb, that's Bergin stressor factor, which is 4c plus 2 over 4c minus 3, and c equal to the coil mean diameter over the wire diameter. So the question gave us the wire diameter already, but the question didn't give us the mean coil diameter. It only gave us the outer diameter here. Okay, so this is the outer diameter. Outer diameter basically refers to the diameter from one side to the other side of the spring, right? Okay. So what we have to do is we have to calculate the mean diameter based on the outer diameter, and it's very simple. Just use outer diameter divide minus the wire diameter here, okay, which is 0.03 inch. So that gives us essentially the capital D over small d, which is 0.03 over 0.006, which is equal to 5. Okay, we got our C value. Then we'll be able to get our Kb value. So now the Kb equal to 1.294, okay, based on the C value here. Okay, so we figure out a Kb, figure out the capital D, and then figure out the also the wire diameters given. The next thing is the load F. Okay, how much load on the spring at here? Okay. So what we're talking about here is the condition when it's fully closed, right? Completely closed. So basically, it's how much force do you need to completely close this spring at here? Okay. So what we do is we have our initial free length given. Okay, free length given. And if we can find out the solid length, or the length when the spring is completely closed, then we'll be able to find out the total deflection of the spring, right? We can use the total deflection of the spring multiplied by the stiffness to get the force. Okay? So that's the idea here. Okay. So the question have NT is 40. To calculate the solid length, if you look at the solid length at here, okay, so we need to calculate solid length based on the formula given in this table 10-1. So which column do we use then? So the question tells you it's the type of spring is square and granite, so we need to use this column here. And solid length is D times NT at here, right? D times NT. Okay. So that's what we going to use this formula here for the calculation. Okay, so the LS equal to D times NT, which give us 0.24 inch. Okay, 0.24 inch. Then the total deflection is the free length minus the solid length, gives us the total deflection, okay, when you fully close the spring. This deflection multiplied by the stiffness will give us the force, right, the external force. So what's the stiffness? And stiffness has this formula here. Okay, that's the stiffness formula. For the stiffness formula, let's take a look at what do we have, what do we not. Small d, capital D, we already have it. capital G is the shear modular, so we have to find it out. And the NA, right? We don't have it yet. So NA here, if you recall that, what does it represent? The total number of acting on the coil, right? So NA here, for this type of spring, for the square and grounded type of spring, the NA from table 10-1, NA equal to NT minus 2, okay? NT minus 2. So that's where you can find the NA value, which is 38, right? 38. The G value is the shear modular here. So the G value, that you get it from table 10-5, okay? And here's 10-5. This is 10-5. So we're looking at a music wire, and the G value actually takes a little bit of difference. Depends on the wire diameter. So that part you have to be very careful. Look at the wire. Where is the wire diameter fall into the range at it here, right? And this question is 0.006. So it basically is the first row at here. So the G we're taking at it's the inch series, so G equal to 12 mega psi. Okay, yeah, that's how you do it. If your D is other than the 0.06, if somewhere between this, and then your G actually will take a slight different value here, right? So that's where just be careful there. So G equal to 12 mega psi, psi. Okay, mega psi. So for D equal to 0.06 inch. Okay. So now I can substitute all the numbers over here. You can substitute all the numbers into here. I don't believe you have to, let me just double check here. The unit, you can actually just stick with the units at here to do the calculations. So the results that here give us you 1.895 pound force per inch. Okay, pound force per inch. Okay. You know what? You need to double check if this is all standard units inch. So this needs to times 10 to the power 6 at here, right? When you do the actual calculation. Okay. Okay. So that's your stiffness. And once you find the stiffness now, then we can find the corresponding load, okay, which is K times delta Y, give us 0.74 pound force. This is a very tiny spring. You know, tiny basically means the wire is very thin, right? So a little bit of force, you have a lot of stress on the spring, essentially. Okay. So that's the number. That's the total force. Then I'm going to substitute everything into the stress formula for the spring. So tau equal to KB 8FD over pi d cubed. Give us 338.2 KSI. Okay, the result is this much. Okay. So that's how much stress inside the spring. So now we can answer the question, is it a solid, safe? What do we compare this with? We compare the stress with the SSY, right? And this is only 189, 890. and this is greater than SSY here. So basically means it's not solid safe. Okay, it's not solid safe. So then that begs the question now. If it is not solid safe, what can we do to make it solid safe, right? Yeah. Let's say we're not going to change the material, and what we can do is, right, we can reduce the load F, so that'll reduce the stress, right? Okay. How can we reduce the load F? You look at this one here, is to reduce the load F. So the only way you can reduce the load F is to reduce the number of the value of this deflection at here. And the deflection is based on the subtraction between free minus the solid length. Okay? Yeah. So then basically the question here is, can we reduce the free length, right? So then it will reduce the deflection. Okay? So here is the question at here. Yeah, so basically, so what would be the free length to make it solid safe? So that's the point. And before we look at the free length at here, right? What we can do is we have the shear strength given, and the shear strength, the permissible shear strength calculated. We also have the safety factor given, right? Safety factor given. Use the strength divided by the safety factor. So this will give us the allowable shear stress. Okay, the allowable shear stress. The allowable shear stress is equal to, if you let the allowable shear stress equal to the actual shear stress. So the actual shear stress is 8. So here's a force, right? Here's a force F right here. Okay, here's a force F. And the force F is equal to the spring stiffness times the delta Y. But I'm not going to use the original delta Y, so I'm going to use an updated deflection delta Y. Okay? So essentially, what is the maximum deflection that you could have for this spring here, given the allowable shear stress? Okay? So you can see you have all the parameters, right? You have all the parameters except the delta S, delta YS. So you can solve for this delta YS from here. The solution for this is 0.182 inch. That's the maximum deflection you can have. Which means my updated free length, right? So this free length is equal to the solid length plus the deflection, 0.422 inch. Okay, 0.422. And when you design for a length, you can choose a nominal size from the table next in the next step. But this is the theoretical results for basically the spring at here, okay, 0.422. Is that clear? So that's a very typical spring type of question that I can give you in the final exam here. Okay. Yeah. How do you check the stress? How do you check the safety? And basically plugging all the parameters appropriately, right? Okay. So any questions? Okay. So for the spring part, there are two other sections in my lecture notes, so you can take a look at yourself for your own interest. Basically for non-ideal spring, and also for fatigue loading for spring. Okay? But for the exam purpose, we're going to stop at it here, basically just for the static case at it here. Okay? Yeah. So that's it. That's all we're going to learn for this course so far for this term. Okay? So that's all the machine components. There's one more brake in the clutches we couldn't cover here. It's too much, not enough time here. Okay. Yeah. Okay, so I will make use the rest of the time to do a quick review at it here. Okay. So as I said, the final exam is not accumulative here, but it's kind of cumulative because you do need to know the static and fatigue failure theories well enough in order to design for different machine components, right? Yeah. So you're not gonna have a question dedicated to like a static failure or fatigue failure like our midterms, okay? Yeah. But you do have questions that need the theories, yeah, to solve that question. So first, let's take a look at what have we learned basically after the midterm. So here's a number of things. I'm picking up things right away, or basically that are not tested from the midterm here. Okay. Okay, so we look at fatigue analysis under fluctuating loading. Okay. So the keyword is fluctuating. Okay, fluctuating here. So when you see fluctuating, basically, what sort of a sinusoid will kind of jump into your mind, right? It's basically it's the most general type of loading. You have a mean value, you have sigma A value, right? Okay, so I'll talk about that in a little details here. Now this is basically your lecture 9 and 10, okay, from my progress of the lecture notes. And then after this one here, we looked at the introduction to gear. Introduction to gear including basically the gear terminology, the construction of a gear, and how to build a gear, you mean, right? Using SolidWorks, the interference. So basically the contact ratio. So a lot of basic terminologies, concepts associated with the gears. Okay. And we also looked at the gear design. Okay. So for the gear design, we're designing for two different types of basically stresses. One is the bending stress, the other is the contact stress, right? The bending stress, we use the Lewis equation as the basic equation. Contact stress, we use that so-called the Buckingham equation actually as a basic equation. Okay. But when we do design, we essentially used is the AGMA equation. Okay. AGMA equation for the design. Okay. This portion you should look at lecture 11 to 14. Okay. So there's 3 lectures associated with this. After the gear design, we look at the shaft design here. Okay, this is a very important part of the lecture here too. Okay, the shaft design here, including basically how to design a shaft. Okay, for fluctuating type of loading, and also including the K design, right? Yeah, in this portion here. So because the K is an important coupling component to transmit the load from the shaft to gear or from gear to shaft. So how to pick a K the size of the key, the length of the key appropriately. And this portion you need to look at lectures 15 to 17 here. Okay. After shaft, we look at the bearing selection. So I'll look at the details a little bit more here after. So that's lecture 18. Okay, from the bearing selection, so these three things essentially is your project, right? It's the project that you have been doing. And this is what I mentioned when I started the project. I mentioned, often in time I understand you guys separate the task, or basically among yourself. So you do the shaft, I do the gear, and you do the bearing, for example, right? Yeah. So the one that's doing the shaft probably actually has an advantage now, because you understand a little more on the shaft. The one who didn't, and actually just talk to you, right? And you still think, oh, what does the shaft design mean, right? So there's guarantee will be a question on the shaft design, okay? And if you didn't do that part of the project, then this is the time you have to revisit, okay? Yeah. Same thing for bearings here. And a gear, it's a very large component, and it's very tough to test. So I will not test you the gear in the final exam. Okay. Yeah. But I will mention that gear are typically integral part of the shaft system. So the loading analysis from, for example, spur gear, right, which create two radial load. One is WT, the other is WR, right? And those are basically you can directly use it for the shaft design. So that very fundamental loading analysis, right? If the shaft is carrying a gear, basically you did that before the midterm, okay? That you have to know it, okay? Yeah, I won't give you a specific question on gear in the final exam. Is that good? So I will test you or mark or grade you through the project report on your gear design. Okay. Okay, so then we look at the screws and the power screws. This is lecture 19. So this portion is very much like introduction and adhere to different terminologies for screws and power screws. Okay. Yeah. And in this section, we also look at the torque that's needed to raise a load or to lower the load. Basically, the mechanics of a power screw, right? Yeah. So I'll talk about detail. So and then we look at the threaded fasteners. Okay. For threaded fasteners here, essentially. We're talking about the bolts and screws. So in this case here, we're looking for is what's the stiffness of bolted joint. Okay, so if you have a tension joint, then what's the stiffness of the bolted joint, including stiffness of bolt and the stiffness of member, right? So I'll list these things next. And then after this, we'll look at the safety of tension joints. Okay. So this is lecture 20 and 21. Okay, covers this portion of content. Okay. So, and the last two components is the welded joints. We spent 2 lectures on the welded joints, 22 and 23. And the last section is the spring, mechanical springs. So part of the 23 covers the spring, but I'll just label 24. Okay, the lecture number in the lecture is just lecture 24 on the connects. Okay, so that's how much we have learned after the midterm. Okay. Let's go into the details that are here. just for each one of the big sections. Okay, and we'll look at some of the what my requirements is. Okay, not necessarily what I list is what I'm going to test you here. Okay, yeah. So for gear, as I mentioned, from out of this course. Okay, and I need to be very comfortable in communicating with other people using appropriate terminologies for a gear, right? Different circles, dedendum, base circle, involute, all of this, diametral pitch, all of those concepts associated with the gear. Okay, you have to be very fluent. And then force analysis. Force analysis, that's the basic one, which you pretty much actually learn even before the midterm. You learned a little bit here. Essentially, when you have two spur gear, what type of force exists? When you have two helical gear in mesh, and what type of force exists? Right? Yeah. So the helical gear, the difference is you create an axial force, okay, along the shaft axis, and that's basically the difference. Okay. And of course, I mentioned about AGMA equation, okay, for stress and strains. Okay. So if you're designing a gear, okay, and this is a very common design process, and you choose AGMA equation as the guiding tool, so then you have to come up with a whole bunch of basically values for different parameters, right? Yeah. For the strains, okay, it's not a typical ultimate strains or yield strains, and this is where, if you recall that you have a stress numbers, right? So basically stress numbers or contact numbers. You can find these numbers through tables or figures, okay, and you can compare the strains and stress to come up with this conclusion, basically. Okay. So that's the gear. Okay. For shaft, okay, as I mentioned, basically we're looking at very common type of situation. So that's basically fluctuating stress. Okay. The fluctuating stress ultimately is caused by fluctuating force or torque, right? Force or torque, which basically means you have, in general, you could have all of the four components at here. Okay. Fluctuating moments will give us the sigma A, sigma M. Fluctuating torque will give us a shear stress, tau A and tau M here. Okay. Yeah. And then what we typically do is we combine basically all of them together here. So we have our so-called combined loading, right? This is basically combined loading here to give us sigma A prime, sigma M prime, using the von Mises stress formula, okay? D theory essentially. Because we're ultimately wanting to use the fatigue loading failure criteria. Those Goodman lines, ASME, elliptic, right? So we in that formula, you cannot plug in both things together. You can only plug in consistently just the sigma. So that's why from here you need to come up with this sigma A prime and a sigma M prime. Okay? Yeah. And then there's failure theories, right? So all of the different failure theories that you can use. Okay. So the failure theory will give us a diameter here, minimum diameter basically. So whichever I have a handout given out to you guys, if you recall that, right? There's a handout for the calculation of the shaft diameter D based on the different basically failure theories. Now you actually can bring it to the final exam. Okay. So from the failure theory, you can calculate a minimum shaft diameter D. And this process, okay, is an iterative process, because D is equal to a function of D based on the formula, okay, or the failure theory. So you will need to iterate a few steps to converge to a certain value. So in the exam, you're expected to do some iterations, at least maybe 2 iterations, to show the process at here. Okay? Yeah. That's very much different from analysis, right? And one more thing is, don't forget this yielding here. So basically the first cycle, this is also my requirement for your project. When you do your project for shaft design, you should also check the first cycle yielding. Okay. Aside from all the fatigue failure theories, there's also one more step, which is the static, basic static checking. Okay. And I include the case design under the shaft section. So the case at here, in this portion here, basically, what's the length, right? What is the minimum length that you require to transmit this amount of a load, okay, from one component to the other component? So that's the shaft design, okay? If I have to see this amount of experience, and I find often in time a couple of things, okay, fundamentally. Basically, the concept of this fluctuating stress somehow some people still not quite understanding, especially, you know, the TA, TM, MA, MM, right? What do they mean? Okay, the symbol wise, essentially. Because these things give you sigma A, sigma M, tau A, tau M here, right? Yeah. Okay. So check out one of the class examples. Okay, and I have a fairly detailed Excel solution too, right, for that class example. Okay, so power school. Okay. We looked at the terminologies. We also looked at the torque, right, and the efficiency, okay, and also the different stresses at different locations. So basically, if you have a power screw, here is a power screw body. Here is basically, let's see, the teeth of the power screw, or the thread of power screw, right? What type of stress exists at here? What type of stress exists here or here, right? I had a couple slides actually, okay, in the lecture notes that you had to be able to identify. Okay, you don't require to be able to memorize all the formulas for this, but you need to know basically what type of stress exists here or here or here if you're asked in a multiple choice type of question. Okay, yeah. So that's power screw here, and then threaded fasteners. Okay, some of the details under this. This is a big section right here. This section, the challenge is that with this section is it's not about actually math, it's about whether you can follow the process precisely. There are so many tables you might have to use, right, to find all the informations that you need for the calculation. So that's the part you need to practice to be comfortable with the calculations. First of all, there's a very useful table, 8-7. So that table has give you lots of useful terminologies, like the length of unthreaded portion, length of threaded portion, the grip, the the minimum required length for the bolt. How do you get the height of the bolt head? How do you get the height of the nut, right? So all of this here, okay. Look at there's a handout I give you. I basically collected all the tables required for this portion and I put it in one handout. Okay. You can carry that into the final exam if you want. So now we look at is the fastener stiffness, and this is equation 8-17. Okay. So you can look at what 8-17 is. And we also have the member stiffness. This is equation 8-20. There are a couple of equations, but they're all actually, I think if you just remember one is enough. One equation, basically, that's the equation for one frustum. Recall that, right? If you have one frustum in here, that equation, right? Figure out this capital D, figure out the thickness, then plug in that equation, then you get that the stiffness for the one frustum. And then bolt strengths. Okay, bolt strengths. You have a couple tables, 8-9 to 8-11. Now they're corresponding to different basically standards. There's the SAE standard, ASTM standard, and the metric system. Right. So the three different tables. Okay. Read the question carefully. What type of bolt you're given, then you look up the table to find the proof strengths. Basically. Okay. So this gives you the proof strengths. Finally, we're talking about tension joints. Okay. We're going to look at the static loading only. So in this portion, there is this basically NL, it's a load safety factor. There's also a separation factor. So remember, separate. There's also the simplest factor, which is basically the stress, the simple stress safety factor. Okay, it's three different safety factors for the tension joints. Okay. Okay, so that's the threaded fastener. Okay. And now we have the welded joints. Okay, which we have just finished. Okay, and we covered different symbols. Okay, basically, the welding specification. How do you interpret a symbol appropriately? Now we focus on the fillet weld, right? So you need to understand, given a fillet weld, the labeling, okay, for that type of basically, let's say H here, right? What does it mean essentially? Okay, yeah. For a different type of weld, the label here, the triangle here, may be arranged differently, right? If you recall that example. To calculate the stress, there are two different cases. One is in, another is out. Okay, another is out. Now this is where I have also emphasized you will be tested. Okay, and by the way, assignment number 9 is the self-study, so there will be questions on the weld and the spring. So you should actually study the last assignments yourself, okay, to prepare for the final exam. Okay, yeah. So what does it mean in, and what does it mean by out of plane? That you have to be able to identify very, very accurately. Okay, yeah. So from here, you have a table 9-1. For out, you have a table 9-2. Basically, one is J, the other is I. Right. So as a mechanical engineering, you got to be able to say, what does J mean? What does I mean? This is a I don't think any other textbook will use a different symbols for moment inertia, right? So polar moment is always J. second moment area or moment of area or moment inertia is always I. Okay, so and that's actually directly to this in and out of plane cases. Okay. And then strains. Okay. For the strains, there are a couple of tables you need. Table 9-3 for electrode. And 9-4 for this welding code or permissible stress. Okay, permissible stress. Yes.
These tables don't bring them.
You have, it's all in the textbook.
Yeah, but should we bring them on our cheat sheet or
You-
giving them?
It's in the textbook. You bring your text. It's open book.
Oh, it's
Yeah, yeah. Okay, so I give you an example, right, in a class, how to calculate the permissible stress. So the idea is we consider our fillet weld as a combination of the base metal and the electrode. So you need to find the material property for all of the three members first, then you find the minimum for each one of them, then you calculate based on this table 9-4. Okay, so one is 0.3 SUT, one is 0.4 SYT. Okay, so then the minimum of these two will be the permissible stress, which you use that to compare with the stress you find from here. Okay, yeah. And again, that here we're going to consider static loading only. There is a fatigue loading in my lecture notes. If you're interested, you can take a look. Okay. So that's welded joints. And the last part, which is the spring. Okay. And I mentioned we just finished the spring here. Okay. Yeah. So for the spring, let me emphasize again. Ask yourself, can you count the total number of a coil given a spring? Yeah. So if the answer is yes, perfect. Otherwise, pick a spring, practice counting. Is that clear? Okay. I don't think I can see anything more clear now, right? So that's it. That's all we have learned after midterm. Okay. Seems to be a lot of stuff, but when you do a review, it just seems to be not, right? Yeah. For final exam, let's just a few things. Still a few minutes. First of all, it's open book. Okay. Second of all, you are allowed to have a formula sheet. Okay. But formula only. Okay, no examples in your formula sheet. Okay, absolutely no examples. If I see any examples, you either worst case is you get kicked out. Minimum is your formula sheet will confiscate it. Yeah. I was about to say yes. One page double-sided things should be fine. Yeah. Okay. Yeah. Similar meaning tough, because other type of textbook might not have exactly the same kind of appendix we have, right? I mean, you could print appendix and then bring another textbook. Yeah. So you could write into, I don't know, right? I don't know how prepared you will be for the exam, right? So if you're well prepared, you may actually not need to flip through the textbook. All you need is just use a table to look up for the numbers, right? Yeah. You are allowed to print pages, but you're not allowed to print the whole textbook. Is that good? Yeah. Yeah. I did have a case a couple years back. The student printed the whole textbook, which I allowed, right, unfortunately. But then he inserted some assignment answers in the printouts, which I found it out, right? So that's absolutely not allowed. Okay. Yeah. Calculator, anything is good. Okay. And you can year mark your textbook. That's okay, right? Yeah. But I don't want to see is you've probably never seen that happen. I don't want to see is people write so many things at the spaces in their textbook. Okay, that's I would consider if you write a whole assignment solution in your textbook spaces, that's not allowed either. Okay, yeah, yeah. Sorry. Yes, the class handout basically means like the summary on the failure theories, like the handout for the fasteners, right? All the tables, specifically from textbook. Yeah, you are allowed to do that. Yeah.
And all of them are interconnected. All the handouts.
I believe so. Yeah. If not, let me know. Yeah, there's a lot of things. Kind of lost track sometimes. Yeah. Okay. What else there? Oh yeah, from a preparation point of view, right? You have been with me for a while, so I would strongly recommend you always look at assignment questions as sample exam type of a question. Okay? Yeah. So those are basically samples, okay, for the final. From a preparation point of view, you could start either way. You could start from assignments, or you could start from reading the lecture notes. There are some more examples in the lecture notes. Okay, there's also tutorial notes. You also have the videos. Okay. I don't think you're a shortage of resource for the preparation here. Okay, yeah. And I'll be here. I'm not going to go away. Okay, so our exam on the April 23rd. Check out the time and the dates. That date is 23rd. Check out the time and location yourself. All right? Yeah. So the exam is 3 hours. You should expect 2.5 hours at least to finish the exam. Okay, from my past experience. Some students finish 2 hours. Yeah. Just the material after midterm. Yeah. There will be multiple choice. There will be single questions. I haven't decided how many yet, but roughly maybe there will be at least 4 big questions. Right? Judging from what I just reviewed here, when I say must tested, how many did I just say? Shaft? What else? Tension joints, right? Springs. And I lost track of myself too now, yeah. Pardon me? Balls, yeah. Welded joints, right? So welded joints, springs, shaft, and tension joints, yeah. Right. That's already 4 questions, isn't it, right? Yeah. Yeah. I didn't skip bearing. Oh, you need catalog? No, you don't need to. Yeah, you don't need to. If there's a calculation, you don't need any catalog to look up to. Yeah. Any other questions? It's all good? Last thing, peer review. Okay, you need to get the mark, right? If you don't do it, you don't get the mark. The deadline for that is April 9th. Okay. And when you submit the report, please drop it off at my office. Okay, because I don't have the keys for the drop box. If you already done it, and then that's fine. I can ask the TA to open the box and then collect for you. Okay. And also teaching evaluation. Okay, so I know some of you did it already, but 20% is a bit of a too low. 50% probably would be a true reflection. Okay. Yeah. All good. All right. Thank you, guys.
good example or like explanation? Are we allowed to print that out?
It's already in the textbook.
It's already in the textbook.
Yeah, what do you mean bring that?
So because I don't have the textbook, I'm just planning on printing
Oh,
out the tables, right?
oh, okay, okay. Yeah, if you want to bring
Useful
that.
pages. Perfect. Thank you.
You said we don't need the bearing catalogs. Do we need any of the tables for bearings in the textbook?
I will give you the message. Don't worry about that. I mean, if it's in a textbook, you can also look it up.
Because I'm just printing off.
Oh, you're also printing out textbook. Oh, well, that's a
Wondering if I
problem.
should print off any bearings.
Don't print a catalog. No. Just some catalogs that maybe, like, remember that combined loading, right? The axial loading and, right? So there's a table you use to either find the bearing. So that would be my need.
Okay, yeah.
But the bottom line, what I wanted to do to you guys is I will try to simplify the situation, right? I really hate sometimes for you to flip through textbook find the same. So I could just say, go find the table, right? And actually will tell you the table to look. Or I even just put the table right? To simplify the And for those of you who don't, I think you asked me, I'm not sure you asked me, right? You did. I will bring another copy. So far, somehow, I remember there are 3 or 4 students reserved, but only 3 students picked the textbook. So I will bring some extra copy textbook with me, right? And I could use it until somebody else asks for it. Yeah? So, but you should print out something for yourself just in case.
Thank you.
You said, like, do we have multiple choice?
Yeah, we do. I mean, single choice, not. Yeah, we do.
On the final exam?
Yes.
Single choice, is it like short answer?
No. Multiple choice, right? That's not.